All right, let's talk about reference frames. We are in the branch of mechanics called kinematics. Kinematics. And in this branch of mechanics, we're interested in the study of motion without regards or concern for the forces causing that motion. So kinematics, the study of motion, without the concern of the forces causing motion. All right, so we're just interested in the movement itself. Okay, now in order to quantify movement or motion, well, I guess I should say movement is a change in space, change in space in some time period. And we can use motion to mean the same thing. So we're describing some motion, we're talking about movement, change in space, change in position in some time period. In order to quantify that movement, we need a reference frame. And a reference frame, all I mean is to set up what you've probably looked at in math or maybe high school physics or even physics in college, a coordinate system. And in that coordinate system, we have different axes, the X or the Y, or maybe we say horizontal and this is vertical. And maybe we even have a third dimension, like a Z axis. The key with these three axes are that they are orthogonal to each other, meaning they are at 90 degrees from each other. So these two, the X and the Y, are 90 degrees from each other. The X and Z are 90 degrees from each other. And the Y and Z are 90 degrees from each other. So I'll put a little box here to represent that. Now it's a little tough to draw 3D on a 2D piece of paper, but the Z-axis is in essence coming out at the camera. And if we have an object that we're tracking in space, we would put a dot there to represent that object. And then we could describe the location of that object using our three coordinates, X, Y, and Z. And I would identify where those three axes come together as the origin, or 0, 0, 0. And what I now have is what's called a Cartesian coordinate system that I can locate this object in this reference frame anywhere this object moves. And so I can actually assign a time here as time 1, and then I can put x1, y1, z1. And I can now identify the location of this object relative to this reference frame. When this reference frame is fixed in space, that means we're not going to move it, then we call that a global reference frame. It's not going to move. It stays there. So if this was in the laboratory, I would put this spot, this origin of these three dimensions in some specific location in the laboratory. Or if I'm doing a seating chart in a classroom, I could call row 1, seat 1, the origin of my reference frame, and then I can have rows of seats and I can have columns of seats, and I can identify the location of every seat and therefore every student in the room. But what I end up doing in this setup is I start creating a way to track this position of this object, and I would track it for some time period, the X coordinate, the Y coordinate, and the Z coordinate. So time, this would be X1, Y1, Z1. And then if this object moved, let's put it over here at T2, and I would now have X2, Y2, and Z2. And I'd have time 2, X2, Y2, Z2. And these are some numbers based upon whatever set of units I assign to these axes. And I would just continue this down. And I would track that object as it moves through space, wherever it's moving. And I can quantify that. And I can quantify it given my global reference frame. All right, so what's important though is that that's not the only kind of reference frame I can use. And I can also use other coordinate systems other than a Cartesian coordinate system. For the most part, in this class, we are going to use our Cartesian coordinate system, which is your standard X, Y, and Z setup, where those three axes are 90 degrees from each other. There's other systems to use and other reasons for using other ways to track an object in space, but this is what we're going to do. In this, when it's fixed in space and does not move, it's a global reference frame. Now that's in contrast to what we would call a reference frame that moves in space, and that becomes a relative reference frame. And so now if I would use a relative reference frame if I'm doing some tracking of maybe a person, and maybe this is just the lower extremity of the person, where I can assign an X, Y, and Z to, I'm going to do that in dotted lines. I'm just going to do two axes. Maybe I put the origin of the axis on the knee joint. And now this becomes a reference frame that moves with the person and moves as the knee even flexes and extends. And this becomes a relative or local reference frame, meaning it's not fixed in space. It's going to move with the person. And so as we look at the knee over here, maybe this is another reference frame with that joint, and maybe another reference frame with the hip joint or with the origin at the hip, something like that. Those are local reference frames. And we use those, especially when we start looking at angular kinematics. But for the most part, most of our kinematic work will be done with a global reference frame, meaning it's not going to move. And we're going to have three axes that are at 90 degrees of each other, which is a Cartesian coordinate system. And then we track that object in space and then create a database of values where at time 1, we know the position of that object. At time 2, we know the position of that object, and so forth. And then what we do when we start doing an analysis, rather than work in 3 dimensions, we get super lazy. And what we do instead is we deal with 1 dimension at a time. All right, so let's say that I have my 3 dimensions here, X, Y, and coming out of the board or out of the table, Z. And let's say we're going to track that object in space as it moves. And I'm just going to connect the dots here. And each one of these dots would have its own X, Y, and Z coordinates. X1, Y1, Y2, Z2, X3, Y3, Z3, and X4, Y4. I can't talk and write at the same time, Z4. So this would be time 1, time 2, time 3, and time 4. And whichever way this object's moving, we will track it. But rather than stay with 3 spatial dimensions, what we will do is we will take these 3 dimensions and we will break it up into 3 different analyses. And the analyses will be looking only at the movement in the X direction versus time. And I'm going to put seconds here now. And then the second analysis will be to look at the Y position versus time. And then the third analysis will be looking at the Z dimension versus time. So in our work, we will do 3 analyses from a standard X, Y, and Z coordinate system, reference system. Now, maybe we're really just interested in how the object moves in the X direction, in this direction, versus time. Maybe that's all we're interested in, and maybe we don't even do these 2 other analyses. Or maybe we're interested in the Y dimension versus time. So just how this object is moving or in this vertical dimension here. Or likewise, if we want to look only at Z. We don't have to do all 3 analyses. We may only do one or the other. And throughout the semester, we'll talk about that. We'll talk about the vertical movement of the person during a counter movement jump. Or we'll talk about the horizontal movement of the person during running. Things like this, okay? But the key here is we can do 3 analyses with each dimension plotted against time. And the advantage of doing this is then we start to be able to get some information about some of our key kinematic parameters, such as displacement, velocity, and acceleration. We know displacement is change in position, straight line distance between 2 points. Velocity is how fast displacement is happening, and acceleration is all about how fast velocity is changing. All right, we've got some other videos on these parameters here, but I typically just call this position, velocity, and acceleration. And what's nice about plotting out one dimension at a time is we can then quickly discern, we can quickly understand other kinematic parameters when we do this type of analysis. Okay, so reference frames. We've got 2 types of reference frames, the global reference frame and the local reference frame. The global reference frame is fixed in space. The local reference frame moves with the object that we're interested in. In this case, I drew a person. We're going to use a Cartesian coordinate system, which is your standard X, Y, and Z, where each axis is 90 degrees from the other, so it gives some good unique information. And then we'll track that object in space over time periods, and then we'll take those data points and we'll only look at one dimension at a time. The X direction, the Y direction, the Z direction. So X versus time, Y versus time, and Z versus time. And then we'll get information about displacement, velocity, and acceleration, all from graphing. Okay, thanks everybody.